In this video, we're going to derive an actual useful equation for solving variational problems. Now, we're not going to attack every possible variational problems. That's too big of a task for us. But the subset that we're going to choose will be sufficient for solving the mechanics problems that we want to use this calculus for. So we're going to have a functional in general. And it will look like this. It will be s, which then takes some function y. And you're going to say that that is defined by the integral going from some xa to some xb. And then be integrated over some function f of y of x, y prime of x, and then also x explicitly dx. So f of y, y prime, and x is known in principle, although we're not going to specify it when we do the derivation. But what we're looking for, what we're trying to determine, is y of x. Okay, so that's our problem. Now, before we go about attacking that, I'm going to prove an intermediate result that will be useful at the end here. And that is known as the fundamental lemma of the calculus of variations. Okay. And it states the following. Let, in at least one version of them it is, let f of x and g of x be continuous functions. On the interval that goes from a to b. If the integral from a to b of f of x times g of x dx equals 0 for all g such that g of a equals g of b equals 0. That is, the function g will vanish on the endpoints. F doesn't have to vanish at the endpoints. If that is true, then f of x is equal to 0 on this interval. Okay. So this turns out to be a pretty important result. Okay, let's go back to prove that first. So it turns out to be relatively easy. Let's say that we have okay, so let's say that we have f of x, and it can be any function. We're starting out here at point A, we're going to point B, and f is some continuous function between the two of them, between the 2 points. Now let's choose g of x without any real restrictions. Well, actually, let's be clear. First of all, f doesn't have to start at 0, nor does it have to end at 0. So let's not make it do that. So this is f, and what I'm going to do now is choose g such that it has always the same sign as f. That's the only restriction we're going to place on it. So this is g now. Like that. That's g. So if that's true now, if f of x and g of x always have the same sign, that means, of course, that f of x times g of x is going to be greater than or equal to 0 on this interval, right? So This then gives us that the integral of f times g on the interval from a to b has to always be greater than or equal to 0, right? And the only way that it can be exactly equal to 0, if we haven't picked g to be 0, and we are free to choose g any way we like, remember, as long as it vanishes at the endpoint and it's continuous, then the only way this can actually be equal to 0, since the argument here is greater than or equal to 0, is if the argument is 0 everywhere. So we have the integral from a to b, fx gx dx equals to 0. That corresponds to f of x times g of x equal to 0. Since g of x is not 0, this gives us that f of x equals to 0. That's what we wanted to prove, right? Okay, so that's the fundamental lemma of the calculus of variations. So since it's kind of important, I'm going to take it and put it up here in the corner, and then we'll leave it there, and then we'll use it when we need it. Okay, so once again, we're looking at this functional. Okay, and we want to optimize this. So what we're going to do here, we're going to say that y of x, that's the correct solution. And y of x is then some other solution, or some other function that goes from the point A to point B, but otherwise doesn't have anything in common with y. But what we do have is that y of xa equals little y of xa, and y of xb equals little y of xb. So if you were to plot this then, we have a starting point A and an ending point B. And let's color code this a little bit. Let's say that the blue curve here, that's y of x. And then this red curve here is capital Y of x. Okay, so you can see that they start and end at the same place. So there's some relationship between the two. We will have in general that y of x equals little y of x plus some other function eta of x. And because of the way we've done things here, we have that eta of xa equals eta of xb equals 0. Okay? So let's now introduce a parameter that allows us to vary the difference between capital Y and little y. So let's say that alpha varies the difference between y and y, right? So what we really get is that y of x equals little y of x plus alpha times eta of x. Okay? Now, alpha eta of x is sometimes written as this little delta y, it's known as the variation of y. Because that's essentially what it accomplishes. You have the correct solution, and then you add some variation to it, and you get something that is a little bit away from the solution that you're looking for. So let's now write down the functional again that we're looking for, or looking to optimize. We have s of capital Y, and that's equal to the integral now of f of capital Y prime, as well as x. All right, we can rewrite that. Like that. And the advantage of doing it this way is that we now have what is a function of y for sure, but it's also a function of alpha. And that makes it possible now to actually do things that we are used to, like taking derivatives, right? So for instance, we'll end up taking the derivative of this function f in here in a minute. So I'll just note that if we do take the f, the alpha, then by the chain rule, that's just going to be equal to eta times the f dy plus eta prime times the f dy prime. Right. So if I then want to calculate the s d alpha, that amounts to taking the derivative of this integral, and since the integration is over a finite interval and the function in here is continuous and well behaved, I can invert derivation integration. So I can take the derivative inside the integral sign, and I get like that. Now what we really want is to set this derivative to 0, right? If we do that, then we know that at least for the particular eta that we have picked, then we have a maximum or a minimum, or at least a stationary point. And then if we can make an argument that that's true for every eta that we can reasonably pick, well, in that case we have a general formulation, a general solution to our problem, right? So we're almost there. We just need to recast the second term on a slightly different form here. So we're going to take the second term of this integral, and we're going to integrate by parts. So we have the integral from xa to xb of eta prime the f dy prime dx. Okay, that's integrating by parts. So basically I take this term and I take the primitive function of it there times this one unchanged minus the integral of the primitive function of this term times the derivative of this term with respect to the integration variable, which is x. That's integration by parts. Now this term here, we know what it is because, remember, we just fell outside here, but we said that this variation here, this variational function eta, is actually 0 at the endpoints. So at xa and xb, eta is 0. So that means that this whole thing is 0. So you're only left with this. So that gives us that the s d alpha and that has to be 0. And in fact, for S to be optimum, or for S to be stationary, this must be true for all etas. All etas, that satisfy the fundamental criteria that it has to be a continuous function and it has to vanish at the endpoints. All right, so let's now take a look at the fundamental lemma of a variational calculus that we proved earlier up here. So we can see now that this looks very similar to the situation that lemma deals with. Eta plays the role of g. It is a continuous function that vanishes at the endpoints. And this function in here plays the role of f in that lemma. So we know that therefore if this integral is 0 for all etas that vanish at the endpoint and that are continuous, then this here must be 0. Okay. So we arrive then at this result is known as the Euler Lagrange equation. And it optimizes or at least it hopefully optimizes it. What it really does, it tells you where there are stationary points in this functional. Now, it doesn't tell you whether these are minima or maxima or neither. Turns out you have to do a bunch of other tests in order to do that, but we're going to be lucky. It turns out that for the application we have in mind in mechanics, we don't ever have to do that. So this is the fundamental result. This is what we're going to use, this differential equation, in order to optimize functionals on this form. And in the next video, we'll treat a couple examples of this.